In this problem, we will be discussing the solubility in water of the molecules that I drew below. Notice that all of the molecules are about the same size of molecular mass, but point is, notice this is a cyclopentene, but it has a substituent. But all these are cyclopentenes with some substituents. Cyclopentene because we have a double bond, right? And so here you can say 1-methoxy cyclopentene. In this will be, I need to do 1, 2. When I'm numbering the alkene, I must do the consecutive numbers to the 2 carbons on the double bond. So 1, 2, so you don't do this. This is not part of the double bond. So 1, 2, 3, 4, and 5. So this has the acetyl group in carbon 3, and it has in 2 metals in 1 and 5. So I can say 3 acetyl, and then I'm gonna have 1,5 dimethyl, and I'm gonna continue the name here, cyclopentene. But functional group, I'm interested in knowing the difference in functional group. Here I have is another cyclopentene, but I have an alcohol. So let's draw the alcohol here more explicitly, because what we're trying to do again is identifying intermolecular forces. These are my solutes. All of these. And I'm trying to dissolve those in water. So this is my solvent. And I know that I have intermolecular forces within the solvent itself, and the strongest being hydrogen bond. That we have seen previously. Again, a network of hydrogen bonding that we can do. All right. And the point is, when you're dissolving a solute in a solvent, there is enthalpy term and entropy term. And also within, it's like you need to create a cavity in the solvent, breaking some of these intermolecular forces to make room for the solute. And you need to compensate with new interactions between solute and solvent to compensate for that. So you want them to be about the same energy, at least to be able to overcome. So here we have a very strong interaction. Let's see if we can replace it with something similar between solute and solvent. This is what is going to make the enthalpy of solvation favorable, if you're able to compensate for that. And again, we always remember all the processes, phase changes, dissolution, reactions, etc. We talk about spontaneity, so where it is favored in terms of delta G, so give free energy, and that has a component that is enthalpy and entropy. So I'm going to write that down here, and let's remember this is delta H minus T delta S. The term that I'm talking about replacing intermolecular forces is the delta H of solvation. The delta S has to do with the degrees, say, disorder, degrees of freedom. And we're going to be disorganizing somehow the solvent as we introduce the solute. Although there will be reorganization. Here's somewhat organized, but when the solute goes in there, you create new interaction, and it will create a new organization. But the largest term that I'm interested, so essentially entropy of mixing is favorable, so entropy increasing, but we're going to pay attention to the enthalpy term. And again, if here I need to break an important interaction, which is hydrogen bonding, I'm trying to see what is that we have in the solute. Can we replace those interactions by some interaction favorable between and about the same energy, right, between solute and solvent? Let's see if we can do it considering the intermolecular forces. So here this molecule, alkene ether. So here I have a dipole here in that direction. So of course I have, I'm going to write this down. So low non-dispersion forces, check mark. And also here I have low non-dispersion forces. And here of course I do too. Now next interaction is dipole-dipole. So increasing strength. And I do have a dipole. If you add those two vectors, you have a net dipole moment there. So I do have that. Here you have even larger dipole. Here, let's recall that this is like that, the dipole, but you also can draw the resonance structure. That explains why is that even more polar. So I'm going to do R and R, so any ketone. Okay, so check mark to dipole-dipole as well. But a stronger interaction, probably this than that. So I'm going to say stronger. And now, low dispersion, this molecule is an alcohol. Of course, we'll have dipole-dipole. Because here you have this dipole and another dipole here, net dipole over there. When you add those two vectors up, so check mark here. And the third type of interaction is hydrogen bonding. And again, this is my hydrogen bonding. We have to identify in the molecules. To be able to form hydrogen bonding, I must have hydrogen attached to either oxygen or nitrogen for the most part. Of course, with fluorine also works. But in organic molecules, this is what we will be looking. And so do I have possibility of hydrogen bonding in this molecule? I do not, because here I have 3 hydrogens, but they are attached to a carbon. Same here. And here you don't have a hydrogen. So no H is attached to O, so hydrogen bonding, I'm going to cross it. So I don't have that. Next, within that molecule. So those are the interactions. I'm breaking that and forming new interactions. Remember that. Now here, in this ketone, well, I have 3 hydrogens there, and I have 1 here, but those hydrogens are attached to carbon. So nope, no hydrogen bonding. I don't have those H's, right? Hydrogen bonding, I'm crossing that. Finally, the last molecule, I do have this. So it's capable of doing this interaction. So hydrogen bonding. And so we would expect, due to the strength of the interaction, that the boiling point actually should be higher here, breaking those molecules apart to go from the liquid to the gas phase. So higher boiling point here, and then this, and lastly that. But now here we're talking about solubility. This molecule should be the most soluble because here you have a type of interaction that is similar to that. In other words, when the solute becomes in contact with the liquid and the molecules disperse, you're replacing this interaction with new interactions of the same type, hydrogen bonding. So that should be the most soluble in water. Also, we have about the same number. We have the same number of carbon, but here I have one more. This is 6. And this is also 6. So 6 carbon, 1 oxygen. So about similar molar mass in similar low dispersion forces. Dipole is here, stronger here than here. But again, this has this interaction that's hydrogen bonding, similar to what I have in the solvent. So this is the one that's going to be most soluble.